So we've talked about asymptotes, we talked about continuity, and we're going to change gears a little bit. We're going to kind of go away from limits just for a little bit, kind of. And we're going to talk about slopes, okay? And we know slopes from back in algebra. Slope is like the pitch of a line, okay? It's the change of your y coordinates on a line, which we can do using a triangle, meaning change, over the change in the x coordinates. And if you had 2 points, x1, y1, x2, y2, you know this formula for slope, y2 minus y1 over x2 minus x1, right? We use the letter m for slope. But we need to be comfortable with this formula just using function notation. If I have 2 points a, f of a, and b, f of b, the slope of this line would be f of b minus f of a divided by b minus a. Right, and a line doesn't necessarily just stop at the 2 points. We can have lines that, you know, extend forever and ever and ever in either direction. Right, we can pass through the 2 points, and there's my line. Okay, it's not just a line segment, it's a line that goes on forever. All right, well, now let's talk about something that seems different but is not. Average rate of change. The average rate of change of, let's just say, a function. And here is a function. We will use AROC for short. AROC, average rate of change. The average rate of change of a function is just going to be the change in your function values divided by the change in your interval. It will tell you, on average, how much you're moving, if we're talking about a function, how much we're moving in terms of our y's for every 1x. So are we going up? Are we going down? And on average, how much are we moving up or down for y's? How much our y's are changing for every x, for every 1x, we can say. All right, so let's look at our function, and let's just take 2 points, 2 random points, and find the average rate of change between those 2 random points. So let me just move this down a little bit. So I'll say we have this A and this B. We'd have this point here and this point here. And this would be f of A, and this would be up here f of B. Okay. Well, the change in my function values would just be the difference in my y values. The change in my interval would just be the difference in my x values. Well, what is this? It's just slope. It's the slope of the line that connects the 2 points that we're talking about. So actually, if I want to find the average rate of change of a function, I just need to find the slope of that line that connects to the, connects those 2 points. This line is called a secant line. You're familiar with secant lines from geometry as a line that passes through a circle twice. We will say a secant line, in terms of just random functions, is a line that passes through two distinct points that we're looking at. Now we can see that this line may pass through the function multiple times, more than two, but we're just talking about these 2 points, and this is the line that connects it. Okay, so turns out the average rate of change of a function is the slope of the secant line. Now, let's say this slope here was equal to, I don't know, 1/2. We would say, on average, my y's are increasing by 1/2 units for every 1 x unit, okay, between these 2 points. On average, my y's are increasing, because this is positive, by 1/2 unit for every x unit, for every 1 x. And the x's were going like to the right always. We typically will talk from left to right. Okay. Now, this isn't saying that my function is always going to be going up 1/2 from left to right. Notice my function goes down and then it comes back up. However, it will go down and then it will go up quicker than it went down. So we end up at a point higher than where we started, which is why on average we went up. Does that make sense? Okay, good. Well, yes, question. No, it's just a different word in a different context. Good question, though. It does not relate to the trig function secant. Okay, I could give you a function and ask you to find the average rate of change of the function. So the function is x squared minus 2. I want you to find the average rate of change of the function between -1 and 3. All you would need to do when asked this question is to find the slope of the line that connects those 2 points, which means you need to find the 2 y coordinates and use the 2 y coordinates and the 2 x coordinates to find the slope. So go do that and check your answer with a neighbor. So in this situation, on average, this function is increasing 2 y's for every x that we move to the right. Okay. However, if you look at the function x squared minus 2, you know that it will go down between -1 and 0, -2. So the function does look like this and then comes back up. So we do go down and then back up, but on average we're going up that much. Okay. Well, what we're going to get to is, how do we know what's going on, say, just at -1? How do I know what's going on just at 1? How can I tell if my function is going down or going up, and by how fast is it going down and up at a specific location? Okay. we're going to use the concept of average rate of change to help us figure that out, okay? But before we get to that question, we need to kind of talk about something that will hopefully help you understand this concept of what's going on at a particular location, okay? Which is why we like to relate things to the real world, and which is why calculus and physics go really hand in hand. We'll have a lot of questions that deal with physics, and what you will hopefully find out is that calculus will help you better understand physics that you took last year or are taking this year. And we will deal with position, velocity, and acceleration strictly, so you don't have to worry about work or force in this class. But straight line motion, position, velocity, acceleration is important, okay? Position, we typically use the function x of t, where t is in time, and x of t is meters. Could be feet, could be some sort of thing, okay? Very, very important to understand what position means. Position is just where you are located, not how far you've traveled. Okay? We will use a table of values to help us understand things right here. Okay, so if you want to copy down that table, please go ahead and do so. We'll use it for a couple extra examples. Now, a table of values is just a distinct set of points, right? 1, 2, 3, 4, 5, 6 points. And in this situation, we are given time in t. This would be kind of seconds. And we're given x of t. This is our position. This is meters. Position. Okay, now at time 0, my position is -2. This does not mean that I've traveled -2 meters so far. It does not mean that. All it means is that when I start a stopwatch, right as I'm clicking the button, this is my location. That's it. Okay? Now, stopwatch is rolling, but we don't know what's going on. When I get to the 10th second, I'm at position 5. So, at the 10th second, when my stopwatch reads 10.000000, infinite zeros, I'm right there. What's really, really important is that between this 0th second and the 10th second, I have no clue how far I've traveled. Because we don't have the information in between those 2 points. What could have happened is that when I start my stopwatch, this basketball could have raced all the way over here at the 5th second, and then it came all the way back over here, and then when my stopwatch gets to 10 seconds, I'm back at 5. Right? It could have gone back and forth 20 times, and then by the 10th second, you're at 5. Okay? We don't know how far we've traveled. We don't know our distance. However, we do know what our displacement is. Our displacement is just kind of the change in my position. I have displaced from the 0th second to the 5th second 7 meters. All right? I started here. At the 10th second, I'm here. I've displaced a total of 7 meters, but I don't know how far I've traveled because I don't have more information. Okay? Very important. Okay? Now, what we will kind of use is our position to help us find velocity, okay? Because we know velocity is not necessarily distance divided by time, but it's displacement divided by time. Displacement can be positive or negative. Velocity can be positive over negative or negative. If your velocity is positive, we say we're moving to the right. If our velocity is negative, we'll say we're moving to the left. We typically use v of t to denote velocity. I just scribbled it out. Good question, though. I don't know. Okay, well, displacement divided by time. How did we find displacement? We just subtracted our two position values, right? So I took my position at the second time, subtracted my position at my original time, and then I had to figure out how long it took me to get there, so I can subtract my two time values. In the previous example, between 0 seconds and 10 seconds, we went from -2 to 7, or sorry, -2 to 5. I had 5 minus -2 over 10 minus 0. So not only can we find displacement, but we can use displacement to find velocity. Well, what is this? This is just the slope of position. So turns out the average rate of change of position, which we know average rate of change of position is the slope of your position. That's going to give you your average velocity. Okay, so I went back to here. I would say my displacement was 7, but I would say my average velocity between 0 and 10 seconds would be 5 minus -2 over 10 minus 0, 7 over 10. That means on average, I've moved to the right 7/10 of a meter for every second. Just like y's and x's, right? Instead of going up and down, now we're talking about right and left. Okay, instead of y values, we're talking about meters. Okay, so I don't know what happened between these two locations. I don't know how far I've traveled, but I just know on average I traveled 7/10 of a meter for every second to get from one location to the other location. Good. We will also talk about acceleration, not much for the rest of this class. We'll just stick with velocity and position. But acceleration, we usually say it's a of t. Velocity is typically in meters per second. And acceleration ends up just being the change in your velocity divided by the change in time. Did you get it? No. No. Well, what's that? V of b minus v of a over b minus a. It's just going to be the slope of velocity. So acceleration, or the average acceleration, will be the average rate of change of velocity. This is super, super important to this class. These relationships that you start with a position function. If you look at slopes of position, you'll get velocities. If we have a velocity function, if you look at slopes of velocities, you'll get acceleration. Okay, slopes. We know slopes. We've known slopes since algebra. Okay. Well, I could give you a position function, and this is just kind of the next step. If I give you a position function and ask you to find the average velocity, you should say, oh, that's a piece of cake. So if this is a position function, so no longer do we have a table of values, we have, any position at any time, could we find the average velocity between the first second and the fourth second? You'd say, yes, of course. I just need to find the slope between those two positions, and that's average velocity. So go do that. We get 2 again? Fantastic. Didn't mean to get 2 again, but we got 2 again. Anybody else get 2? Yeah? Okay. Well, this would be now, instead of 2 y's for every x, we'd say, on average, if my position is denoted by this function, on average, we have gone to the right 2 meters for every second. Okay? Good. So now we know on average. But let's talk about what's going on at a specific location. Let's talk about, am I moving up or down on this graph here at C? If I'm given a table, if I'm given a function, can I figure out what's going on right at that location? Am I going up or down if I'm looking from the left to the right? And then how fast are we moving? Or, going back to this example, can I find exactly how fast I'm moving and which direction I'm moving in at a specific second? Let's look at the 15th second. Okay, so I want to figure out what's going on right here at the 15th second. Let me just highlight it. Now, remember, I'm given position and I'm given time. Position is just telling me where I'm located at a specific time on my stopwatch. At the 15th second, I'm located at this position 20. Do I know how fast I'm traveling and which direction I'm traveling at that location? Just by looking at my information? No, right? Because this is all I'm given. At the 15th second, I'm located here. Okay, kind of approximate what's going on at that situation. Well, yeah, sure. Definitely. I could find maybe the average rate of change, or I could find the average velocity. I can find the average velocity between the 10th and the 25th second. So average velocity between the 10th and the 25th second, because that's the information I do know, I do have. I know that at the 10th second, I'm located at position 5. The 25th second, I'm located at position 25. If I moved consistently between those two positions, maybe at the 15th second, I'm traveling at that speed, that average speed. Okay? So this is a decent approximation. It's the best I can do as of right now. So average velocity is just the average rate of change. So I can just do 25 minus 5 over 25 minus 10. And I get 20 over 15, which is 4/3 meters per second. So I'm moving to the right 4/3 meters for every second. Right? This is my approximation as of right now. I'm saying if I move consistently, if I move consistently from 10 seconds to the 25th second at 4/3 meters per second, so over 15 seconds, I'm moving this quickly. Well, at the 15th second, I will pass through position 20 going at this speed. Okay. Well, what would I need to give myself a better idea of what's going on at the 15th second? What don't I have that I could use to be like, oh, actually 4/3, that's a bad approximation. 10 seconds and 25 seconds, that's just too much of a range. What do I need? Need more values, right? What values could help us understand what's going on right at the 15th second? Like a value where and where?
15 plus and 15 minus.
Yeah, let's maybe go a little bit further away though, and let's say, what if I knew what's going on the 14th and the 16th second? Would that help me? All of a sudden we can add in two values that all of a sudden I just found. I asked the person who created this table, I said, you know what, give me the 14th and the 16th second, and let's see what's going on here. Well, it turns out at the 14th second, I'm located at 21, and at the 16th second, I'm located at 19. Well, that's interesting. That means I actually went from position 5 to position 21, then through 20 to position 19, and then back up to 25. So all of a sudden, things are changing. Well, if I found the average velocity between the 19th and the 21st second, this is going to be a better approximation. So I got, what did I say? 19 minus 21. Sorry, 14th and the 16th second is what I should have here. So I got 19 minus 21 and 16 minus 14. This gives me -2 over 2 or -1 meters per second. So all of a sudden I'm saying, you know what? That 4/3 moving to the right every second, that's not going to be a great approximation where it's going on right at the 15th second. Instead, I'm going to say we're moving to the left 1 meter for every second. This is better. A better approximation. Okay, well, Mr. Folsom, what would give me the best approximation if I had what values? Right, if I had my position not at the 14th second and the 16th second, what if I had the position at the 14.999999999 second? And what if I had the position at the 15.0000000 first second? Infinite amount of zeros, infinite amount of nines. Okay, and maybe I found, using my crazy accurate stopwatch, that my position was 20.01 and my position was 19.98. Well, what is the concept that we've been using where we're talking about something infinitely close to, but not exactly on top of? An infinitesimal, which is an L word, a limit. Okay, we can use a limit to get ourselves the best approximation. So why don't we find the average velocity between the 15 minus and the 15 plus? Well, I can calculate that, right? Because it's slope. And because I'm not talking about one specific location. If I'm talking about just what's going on at 15, if I just tried 15, I would have 20 minus 20 over 15 minus 15. That's 0 over 0. Well, that's a location of a hole, right? That's bad. I can't calculate what's going on right at 15 if I'm just looking at 15. But I can calculate what's going on right at 15 if I look just to the left and just to the right, because we know that we're not going to have 0. We're going to have something infinitely close to 0. So this was 19.98 and 20.01. And we had 15 plus minus 15 minus. And I could use actual values here, and I could actually calculate, and I could actually get a number. And let's say that number is -3. Well, turns out, since we are infinitely close to this location, to this time, that this average velocity no longer is an average anymore. Because we're infinitely close, we actually know exactly what's going on. It's just kind of like thinking about 1 over infinity, how we say this is 0, right? Is it really 0? No, there's some value to it. There is some value. However, there's an infinite amount of zeros before our value. It is so infinitely small that we say it's 0. Well, in this situation, since we are infinitely close to 15, we no longer say that we are approximating what's going on 15. We say we know exactly what's going on at 15. So this is now an exact velocity. Now I know what's going on exactly at that point. And instead of average rate of change, this becomes an AROC, or an instantaneous rate of change. Now, what would this instantaneous rate of change look like, say, on a graph? Yeah, we will see that. So let's say we're looking at this spot 15 right here. This is our information that we were looking at. Well, we started by first using 10 and 20. Now, we didn't use those exact values, but we said this slope of this line, this was a secant line, and this was the average rate of change, right? What did I do next? What 2 points did I look at next? I looked 15 and 25. What was the 2 points that I looked at next? 10 and 25. What did I look at next? 14 and 16, right? Well, if I knew the 14th point and the 16th point, I calculated the average velocity using those 2 points. And I said, okay, well, maybe this will give me a better approximation of what's going on right at 15. So this also was an average rate of change. Gives me the average velocity. Well, the last thing I did was take 2 points infinitely close to 15. And I found the average rate of change between those. Well, let's think about taking 2 points infinitely close together. Can we connect them? Yes, because there is distance. It's an infinitely small distance, but there is some distance, and we can connect them. Now, if I connect 2 points infinitely close together, you're not going to have much of a line, right? Right? It'd just be an infinitely small line segment. But what would happen if I extended them? If I extended that line that I kind of connect. Let me get this one out of the way. If I extended that line, I'll do this in blue, all of a sudden I would see something like that. Right? Just two infinitely close points together, connected and extended. Well, we said that we are connecting 2 points, right? But since they're infinitely close together, it's really like they're on top of one location, right at 15. What was a secant line, which is connecting 2 distinct points, ends up being a line connecting just at one location. Okay? A line that's just touching my function essentially at one location. Even though we have 2 locations, 2 points infinitely close together, essentially it's at one location. That's the whole 1 over infinity is essentially 0. Well, this turns into a tangent line. We know tangent as being a line that touches a circle just once. Well, we'll talk about tangent lines to functions being a line that's just going to touch a function once. We can define that. A tangent line is a line that touches the function at one location. However, how is this tangent line created? We'll take 2 points infinitely close together, connect them and extend them. Because we can do that. Because there is some distance between them. So I say created by connecting and extending 2 points infinitely close together. Okay, secant line, line that connected 2 points. Now, what was the slope of the secant line? The average rate of change of the function, right? Well, 2 distinct points, connect them, find the slope, average rate of change. Well, take those 2 points, make them infinitely close together. We are still using a slope formula to find the slope of this tangent because we have 2 points that are distinct. They're infinitely close together, but they're not on top of each other. Since they're not on top of each other, we can find the slope of it. Okay? However, instead of it being average rate of change, since it's essentially at that location, this turns into instantaneous rate of change. And this can tell me exactly how fast I'm traveling, in what direction, at a specific point. It can tell me how quickly my function is moving up or down at the specific point. If I said that this was -3, I would say exactly when t equals 15, I'm moving -3 meters per second. It's almost like being able to look at a velocity meter, some sort of speedometer that also went into the negatives, and stop my stopwatch and read exactly what's going on. How does my car calculate that? Well, it's calculating some sort of small distance and how much my wheels are moving in that small distance of time. That's just all they're doing. Yes. You can just put the negative sign, it's fine. Okay? So right here, I would know that my function is decreasing at whatever this slope is, units for every x unit. Okay? That's the introduction to derivatives. We don't know what derivatives are yet, but we'll find out what derivative means next class. Now, for your homework, you also will be writing equations of lines, because not only are we going to kind of look at a secant line and look at a tangent line, but we'll be able to create the equation for that line, those lines. So remember equations of lines. The most popular one we will use is this equation, the point-slope form of a line. Now you're going to be very excited with what I'm about to tell you. If you are asked to write an equation of a line, let's say a line that has a slope of negative 2/3 that contains a point 1,4. You just need to plug in your point and your slope into point-slope form, and you're done. That's it. You do not have to solve for y. You do not have to distribute the negative 2/3. You do not have to find a common denominator. You only have to do it for a multiple choice question where you don't see this point-slope form as part of your answers. But for your homework, for your quizzes, if I ask you to write an equation of a line, this is an equation of a line. Notice we have y's and x's, which means we are looking for solutions that are points. There's an infinite set of points that will satisfy the solution. You plot all of those infinite solutions, you get a line. Perfect. If you want to solve for y and you want to plug it into your calculator, well, in some situations, it might be easier just to add the 4 on the end and not have to worry about distributing things, okay? Now we need to practice writing some lines. We will be talking about parallel lines. We'll be talking about normal lines. So a question could be write the line, give the equation of a line that's parallel to this line that passes through the point 1, 2. Well, you need to be comfortable with this form of equation. This is y equals mx plus b. So you can see that the slope of this line is negative 3. That means your new equation must have the same slope and has the point 1, 2. We'll write down the equation of that line. That's going to be parallel to that first line, but it's going to pass through the point 1, 2. Simple. No extra work needed. Now, it's important to know what the word normal means. Normal means perpendicular. Write that down. Now, perpendicular lines have opposite reciprocal slopes. Perpendicular lines have opposite reciprocal slopes. So, what do I mean by opposite reciprocal? That means if a slope is 2/3, a perpendicular slope, this is the symbol for perpendicular, would be negative 3/2. If I have a slope of 2, the perpendicular slope would be negative 1/2. If I have a slope of negative 2, the slope that's perpendicular is positive 1/2. So if I have a question that says I want a normal line to 3x minus 7y equals 10 that passes through the point 1, 5, we first need to find the slope of this line. Then think about our normal line, our perpendicular line must have an opposite reciprocal slope to this line, and then we have this point 1, 5. No, 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 no. Get that stuff out of my face in my class. So, figure that line out. Okay? Be that equation. Now, if I gave you 2 points, you can find this.